Okay, we'll go ahead and get started. Sorry for the delay as they've locked the classroom again. So before I get started, any questions on the documentation and design documentation for your program that's due today? So yeah, I'm expecting something that describes how you're solving it. So pseudocode is one way of doing it. You can have the equations for detecting parallel. So there's a bunch of things you can do. But yes, basic layout, and then for each of the primary methods, right? I expect to see here's how I'm solving that. For methods like basic I/O, I'm not terribly worried about understanding those in the design document because hopefully you can figure the I/O. That's not what the point is, although you have to do that. Other questions? Or did that answer it? Yes? Yes, submitted the Program 2 window. I will actually make another Program 2 window with the final assignment after this one's turned in, but I didn't want to have them both active at the same time just because who knows where things would go then, so I'll keep it cleaner. This should also be in your repo, so especially for those of you who still had at Program 2 assignment some problem with your repo, please make sure you put this in the repo so that I can push on the TA to get him to check that it's done and in there. So there's another question down here, Sam? That's it. Okay. So if there's two of you, if you read the document, I also want to know who did what, because grades for the program, even the design documents, may not be split equally. So if your team said, well, you do all the design documents and I'll do all the coding, then your grades won't be quite split evenly for either half, but that may work out for you if that's where you want it. Okay, so then today we'll go ahead and start talking about eigenthings. First, they were based on the journals. Come on, where's my mouse? Based on the journals, there were a couple of questions, so I'm going to sort of talk about them, trying to answer some of what came up in the journals. So some people struggled with the algebra, some people struggled with geometric, so I figured I'd review quickly before we go into the clicker questions both of those to make sure people have a decent understanding of what we're doing here. So if I have this matrix A on the left, that is a transform matrix, and that matrix, when applied to the phoenix, gives us the second phoenix on the right? So this is a transformation that's going to do some skewing and scaling, right? But it's a non-uniform scaling, so it's going to affect the axes differently. So how do we actually go about getting the eigenvalues and eigenvectors of this? So what's the first step of getting the eigenvalues? Anybody who wants to get some class participation points? Ryan, you've got lots of points. Anybody in the back section? Dakota. Dakota here? No. Okay. So, sort of. We actually can look at it as we take A minus lambda times I, which I can also look at just as, come on mouse, right? Subtracting lambda down the diagonal, and then we're going to take the determinant of that and set it equal to 0. We call that the characteristic equation. That's Bryce. Who just answered that question? Is that Jacob. Oh, okay, so change seats. Okay. So we turn that into the determinant. Remember the determinant we take by doing this sort of pairwise cross product, subtracting them. So that gives us the determinant of lambda squared minus 4 lambda plus 3. And we want the roots of that, the values of lambda that make that equal to 0, which are 3 and 1. And a formula, this one is one I actually do remember because deriving it is more painful than remembering it, so there's always a trade-off in what that is, which is the quadratic formula. So minus b plus or minus the square root of b squared minus 4ac over 2. That gives you the roots of the two solutions to any quadratic of the form ax squared plus bx plus c equals 0. Now sometimes you don't have to use that, you can just factor it by looking at it. Like this one is actually pretty easy to factor, but you can always use this formula for any quadratic. And so for 2 by 2 eigenvalues, you may need to get that. So that gives us the eigenvalues. Okay, now what do we do to get the eigenvectors? Austin, Payne. Where's Austin? No, back there. Okay. Don't know. Logan. Arakai. You also don't know. Okay? Jono. Well, you may or may not get one row to equal 0, but you fill in. So, and I don't know why I'm missing a slide. So I'll use the blackboard. Where's my pens? Should have had a whole other slide here. But, so we started off by saying a minus lambda I, the determinant of that equals 0. Now that I've gotten lambda, right, I know that ax equals lambda x, where x is an eigenvector, right? So I can solve that, or I can solve a minus lambda times I, x equals 0. Right? So this is the homogeneous form of this, right? If it has a solution where one of the rows goes to 0, then we get some choices. If not, it may be completely determined. But we solve for this equals 0. We solve that for x. So we'll actually have more problems going through that, so I'm not going to go through all the algebra right now. But if we do that for this problem, we actually get two solutions. 1 over the square root of 2 times 1, 1, and 1 over the square root of 2 times minus 1, 1. An important point to note, especially if you're watching other places, our book uses a notation which is actually relatively standard, but apparently not used by all sites, including Khan Academy. Eigenvectors can be viewed in one of two ways. If I have ax equals lambda x for some value of x, then a times 2x is equal to lambda 2x. In fact, for any value I put in here, this is always going to be true, right? Because I'm just multiplying both sides of the equation by 2, so it doesn't really matter. So x is actually not unique, right? I can scale it by any constant I want. We want to avoid scaling by 0. That's a bad scaling, but everything else is sort of valid. So the book, like most good linear algebra books, actually wants the eigenvalues, or the eigenvectors, to be normalized so that they're a unit vector. Their length is of size 1. So even though here I have 1 over the square root of 2 times 1, 1, right? 1, 1 is also an eigenvector, because if I multiply that, I'll just get something, it'll be scaled differently. So we want to make sure our eigenvectors are normalized. And so if you're working in problems and you're not getting the same answer as the book, it might be because you forgot to normalize. And there were a couple people in their journals where I think that was the problem they were struggling with, is you kept coming up with an answer, but it wasn't the same answer as the book. You probably forgot to normalize it to get the same answer. So this gives us our two eigenvalues. Now, if I look at this drawing, you'll actually notice I've drawn now, there are two axes drawn on top of it. This is from one of the figures in the book, right? So this is actually showing those two eigenvectors, okay? One is 1, 1 up and to the right. The other is minus 1, 1, which is down and to the right. Now, those are a little bit, again, when I talk about scaling, there's actually the opportunity, I could have scaled the opposite way. I could have gone up and to the left for the second one. Okay, there is one very important property, though, of eigenvectors. Given I have the first one, what's true of the second one? There are lots of people who need some class participation points. If you've never answered, go for it. Joseph. It has to be orthogonal, right? So there really only are two choices, to the left and to the right. Once I know one of them, the other is actually solvable in other techniques. And when we get to high dimensions, we'll talk about that. So now I wanted to go through, the book had another geometric interpretation that two different people, Mimi and somebody else, struggled with. So I want to go over this one. So another way of looking what eigenvectors tell us is that we have a way of looking at everything as a projection. So we have these two axes, okay? Now here, this was drawn with the axis at full length, 3 and 1. Here I'm just drawing the two axes. So if I take those two axes, which are really these two eigenvectors, then if I take some random vector x, I can always express x as a linear combination of these two vectors. They're orthogonal, or orthonormal, in fact. So I can always write anything as a combination of them. So I do that by first projecting onto one of the axes. And for PowerPoint reasons, I projected onto the two axes first, just because I got my animation out of order. And I do that by using a orthonormal projection matrix. If you remember, we've discussed this one twice before. The orthogonal or orthonormal projection projects perpendicular to the line, and I can compute that by taking some vector and that vector transpose and doing the outer product, right? So you do that, right? So we have, in this case, I have 1 over the square root of 2, 1 over the square root of 2 times 1 minus 1 up here, 1 over the square root of 2 minus 1, 1. And then I'm going to put 1 over the square root of 2 minus 1, 1, right up here. And when I multiply them, oops, I want to multiply them, the outer product. I want to do transpose, so 1 over the square root of 2 minus 1, 1. Right? So then I just keep multiplying these, and I get 1, but I multiply this, so I get a half, right? Because I have the square root of 2's there, right? So I get 1 half, minus 1 half, minus 1 half, and 1 half. Right? So that's where that comes from, right? When you take the outer product, where I do R2 times R2 transpose, I get a 2 by 1 times a 1 by 2, and I get a 2 by 2 matrix. Okay? So that gives me an orthogonal projection matrix. And if I multiply that by any particular vector, in this case x, I get this sort of dotted version over here. I can do the same thing for the second axis. I do R1 transpose, and it gives me, again, 1/2 because of the square roots of 2. I actually am going to take 3 of those because I have 3 px1. Why is it 3 px1? So Mimi, do you see why it's now 3x1? This was just how to do the multiplication, right? So that's not going to help, right? But why am I taking 3 times px1? Right, so lambda 1 is 3, so we're taking 3 times that eigenvalue, or so 3 times that, the projection in that direction, plus 1 times the projection in the other side. So that's why I actually have a 1 out here. It's 1 times that because the eigenvalues were 3 and 1. So then I can express ax, which is a times that vector x, as, right, the linear combination of these two, which is this much in this direction and this much in this direction, which gives us this point over here. So I can describe multiplying a vector, instead of just viewing it as I multiplied by the matrix, I can decompose the matrix into a projection in one eigenvector and a projection in the other eigenvector. Now, in 2D, none of this is really exciting. I know a couple of you struggled with what's the real geometric value of this. This seems like it's much more work. And actually in 2D it is. Okay? It might help you have some intuition. What does this matrix do? Because if the matrix A is real and symmetric, then we can look at its eigenvalues and eigenvectors, and it'll tell us what the circle becomes. Okay? The real value of eigenvalues are going to happen, and eigenvectors are going to become when we go to high dimensions. When we get to high dimensions, eigenvectors become really important because we might work in 1 billion dimensions, but of those 1 billion dimensions, only a couple 100,000 might be interesting. Or I might work in 1 million dimensions and only have 1,000 of which are interesting. So when we do some stuff in face recognition, and probably the world's most valuable eigenvector is computed on a regular basis by this little company called Google. Right? And they actually use eigenvectors. That's behind Google search. We'll talk about that when we get to high-dimensional versions of it. But this is really just to give you some intuition and what's coming up, right? And behind Google's intuition came from understanding what eigenvalues were, and that led to forming the company, the better search engine, and everything else that came out of it. So, not likely we will instantly find another high value of those. But I'm going to go back to. So people, can you see the screen well enough this way? No. Okay. I don't have too many other choices. So. No, that's not it. That's even worse. Okay, we'll look at that. No. We'll look at that. Okay, so now we're going to move on to clicker questions. So what's the first step in finding the eigenvalues of a 2 by 2 matrix? This comes from a journal. This should be quick, so we'll give you another 45 seconds. We'll go to a minute. Okay, last call. Okay, so this one, in fact, I included this one because the student who had it in the journal actually got the question wrong. They thought the answer was D. Okay, but the actual answer is B. Find the determinant of A minus lambda I, which is the first step. Right? A minus lambda I determinant gives me the characteristic equation, which is the second step, D. Right, so the correct answer here was A. Find the determinant of A minus lambda I. Question or stretch? No, the correct answer is B. Find the determinant of A minus lambda I. What's the first step in finding the eigenvalues of a 2 by 2 matrix? B. Right, so, well, I'm not sure what you said. You misunderstood. Okay, another question or? No, I have to compute the determinant. So I have to take this, right? So in that matrix example I went through, well, we'll do one on the next one, right? But you have to compute A minus lambda I, and you get a determinant that's got lambdas in it. Once I have a determinant with lambdas in it, now I have the equation. That is the characteristic equation. I set that equal to 0 and solve for lambda. But first I have to compute it. Well, you might look at a matrix and know exactly what its determinant is when you look at it, but most of us compute it. So. Okay, so now let's actually do one. Consider the matrix 1, minus 2, minus 1, 0. Find the eigenvalues. You can chat with the neighbor on this one. There is some calculation, but not much. Okay, we'll give you another 1 minute. Okay, last call. Okay, most people did get this. The correct answer was D. We take our matrix, we put in the lambda, we do 1 minus lambda, we do the determinant. Remember, the determinant is this product minus this product, or AB minus BC, which gives us 1 minus lambda times minus lambda minus 2, right? So we get minus 1 times minus 2, which gives us minus 2. And then from that one, because it's actually so easy to just look at it, you can pull out the equation, but you can look at it and just say, oh, look, right? I actually have here lambda squared minus lambda minus 2, and the roots of that are 2 and minus 1. Okay, so that gives us D. Did anyone solve this one a slightly different way? Okay, so I mean that's the straight out and multiply it. There actually is a trick to any matrix that is diagonal, or sorry, that upper triangular, or in this case, it's sort of almost upper triangular, right? There are some tricks. We'll come back to those later because the determinant of one of those is always a little bit easier to deal with. But okay, so now let's play with some geometry. Consider the following sequence of drawings, right? I'm going to multiply the phoenix by a matrix A, and it's going to stretch by 1.3 and shrink by 0.7 that dimension. So as I iterate this transformation, after a couple times, my phoenix gets more and more distorted. Which of the following are true of that transformation? The eigenvalues are real. The eigenvalues are 1.3 and minus 0.7. The transformation is real and symmetric. A and D, all of A, B, and C. You get 30 seconds. Okay, that's it. Okay, so the correct answer, so does this happen to have real eigenvalues? Yes. In fact, who can tell me what are the eigenvalues? 1.3 and 0.7, not B, not minus 0.7. It's 1.3 and 0.7. If it was minus 0.7, what would the drawings do? So every other one would be flipping, right, along that extra axis. So. Okay, and so the answer was D. It is also a real and symmetric matrix. Okay, so consider this matrix: 1, minus 2, minus 2, 1. Find the eigenvectors of A. you can work with a partner. Okay, the first step is find the eigenvalues. Have people all found the eigenvalues? Did you look back in your notes? maybe we didn't do this one. I did a different example. Yeah, I did this one. No, this is the first example I did, isn't it? Yeah. So just to be clear, the eigenvalues are 3 and -1. If you didn't get that, the next step will not go well. Okay, we're getting closer. I'll give you another, about another minute. Okay. How many people are still actively computing stuff? Okay, I'll give you another minute. Don't want to. By the way, if you have your answers, a couple of you should probably check them. Think about how you check them. Okay, people still working? Last call then. Okay, so the answer was not A. 3 and -1 are the eigenvalues. I asked for what are the eigenvectors, and I said what were the eigenvalues. It's clearly not D, well, that number will keep reoccurring. I'm not sure why. It is not even a vector. So the answers, the choices were between B, C, and D, and E. Okay, so how did you check your answers? Anyone actually check their answers? No? So, Jonah? Right. So we can go back to this property for the eigenvector, stick it in, and if we get this, then we know we got this. So on any question where you're asked to find the eigenvectors, it's pretty easy to check that you got the right one. Now in multiple guess, you could have actually just plugged each of these in and seen which ones worked. That would not have been the way you would be able to do it in the midterm because it will not be a multiple guess in the midterm. You have to derive it. But, okay, so how do we derive it? So first, we're going to, well, that didn't come out the way I expected it. But so for lambda equals 3, we got the eigenvalues. We actually did this earlier. I derived the eigenvalues for you. So we're going to get -1 plus lambda minus 2. We just plug in the value of 3, and then you get the matrix -2, -2, -2, -2. So that matrix is degenerate. If I actually try and multiply it by a shear so that I get rid of the bottom left hand, what happened to the bottom right? It also goes away, right? So I end up trying to solve an equation that looks like 2, 2, 0, 0, or 1, 1, 0, 0, V1, V2 equals 0. Okay, this is a classic thing that will come up. By the way, you know your flashlight is on. This will come up in lots of eigenvalue problems, and maybe that's why Jonah said you want to make it go to have an equation with all zeros. This doesn't always happen, but it happens frequently. So what happens if I go to solve this, right? Well, basically, if I get a matrix like that, it says there are infinitely many solutions, right? for every value of v1, there is a value of v2, and vice versa, right? So I can just arbitrarily choose one. So I'm going to take v2 equals t, or 1, and then v2 will equal minus t. So I get something that looks like a vector of minus 1 and 1. And anything that has that for any value of t will be a valid eigenvector, right? Now, for the other value, lambda equals minus 1, I put that into the equation, and now I get a matrix that looks like 2, minus 2, minus 2, and 2. Right? So if I go to shear this, I'm going to multiply with my shear matrix. What is the shear matrix? Because people, I didn't draw the last one, but what is the shear matrix I would use here? Or what would I do? I mean, if you don't, if so, I was going to say, I forgot that. Many of you said you're still struggling with this shear matrix, okay? That's the way the book presents it. We'll come back to it for a little while. But for a 2x2, you don't have to. How did you solve a 2x2 matrix in high school if you didn't use a shear matrix? You said, what do I multiply and add to make something go away, right? You always try to get rid of a variable. So if I view it as trying to get rid of this variable here, my mouse, if I'm trying to get rid of this one here, I simply want to add the two rows, right? I add row 1 to row 2, and that will make that first item go away. But unfortunately, it also makes the second item go away, so I again get a matrix that looks like something with 0. So after I do that reduction, I get 1, minus 1, 0, 0, right? The minus 1s are just divided by 2 to simplify stuff. And once again, I get something that looks like I'm just going to want that scale, right? So now I want to normalize these to get my unit vectors. So my unit vectors are minus 1, 1, and 1, minus 1, 1. And so that gives me my eigenvalues of minus 1 over the square root of 2, 1 over the square root of 2, and 1 over the square root of 2, 1 over the square root of 2. So the answer was B. So what's the norm? So let's go back to this one. Okay, so if I have minus 1, 1, and I can put in a value of t, but I'll just forget t for a second. What's the norm of that vector? I know this is a long time ago. It's chapter 2. We've covered a lot since then, but what's the norm of that vector? Right? It's the square root of the sum of the two items. So it's the square root of minus 1 squared plus the square root of 1 squared, right, which is the square root of 2. Right? So I do that because I want the norm, I want the eigenvector R1 times R1 transpose, that's a dot product. I want that to equal 1. Right? This gives me a constraint that makes it unique, and I don't have to worry about all the possible scalings. That answer? Okay, quick engagement question. How engaged in learning were you in the last 5 minutes? Last call. Okay, yep, there's enough. We'll do the quick, why not? If you weren't, obviously if you were, but there were enough of you that weren't. I got to balance going too slow for some and too fast for others. So for the don't know, is it like just too early for you guys? Like you need coffee? Okay. Okay, today was definitely too fast. So it's too fast, and again, I'm not holding any of this, I'm just trying to understand how, is it I'm going too fast or I'm not giving you enough time for the clicker questions for that last 5 minutes? So more time for the questions to work through them? Yes? I heard a yes. Okay. More time to absorb the answer. Okay? Do you want me to go back and go through that answer again? Okay? Okay. So all the steps, I'll go through them one more time. So do you know how to get the eigenvalues? I skipped over that entirely. Good with eigenvalues? Right, we did the characteristic equation. Right? So now I have the eigenvalue. I take the eigenvalue and I plug it back into effectively this equation. Right. I have a minus lambda I x equals 0. So I'm going to put that back in. So I'm going to take, in this case I have, well, this already right? So I'm going to take lambda, I'm going to put it back in. I'm going to get 1 minus lambda, minus 2, 1 minus lambda. Right? Now I put in the value of lambda equals 3. When I put that lambda equals 3 and I get 3 minus, 1 minus 3 is minus 2, minus 2, minus 2, just carries along, and 1 minus 3 is minus 2. So that gives me this matrix of minus 2, minus 2, minus 2, minus 2. Now here I did go a little bit fast, right? So if I try and solve that matrix, again, if I just subtract the first row from the second row, I'll get 2, 2, 0, 0. And in this case, the tool I used to actually make these slides, right? I forgot, we also divided the top row by 2 just because it simplifies everything. So I could have actually left that like 2, 2, 0, 0, x equals 0, and now solve this for x. But when I'm going to solve this for x, the bottom row is empty, right? So I can put in anything I want. So if I view this as x1, x2, right? I can choose anything I want for x2, as long as I solve it in such that x1 equals minus x2, right? As long as I make sure that's true, this equation is true, right? The bottom row, doesn't matter what I put in here. The top row, the 2 times 1 minus 2 times the other cancels each other out. So that gives me something that looks like the vector minus 1, 1, sometimes some value t. Because I can put any value of t in there I want. That's where I got the t from. I just wanted to, because some of the people were kept struggling in their journals. They talked about the fact that there's infinitely many of these. There are because of this, right? For all answers, there's always this. But for this answer, it's even worse because for any value of t I put in here, right, I don't get to know what it is. I have to make a choice to make this come out. So rather than doing it this way, another way, which is maybe easier for you to understand, is if I get this equation, let me just arbitrarily choose one. I'm going to say that x2 equals 1. Right? So now I'm going to get 1, and what is the value that x1 has to have? Minus 1. So there's my vector. I arbitrarily choose 1 when I have this system, and I fill in the other answer. Right?
Say subtract the rows from each other. How exactly does that occur?
So I can multiply by a shear matrix that looks like this. 1, 0, 1, 0, minus 1, 1. This adds minus 1 times the first row plus the second row. That's subtracting this row from that row. I'm just describing it a different way because in the journals, again, people were saying, well, you know, this shear stuff is very confusing to me. Can I just do it like I did in high school? The answer is yes. In high school, you would figure out, I multiply by the first row by something and I add it to the second row. In this case, I'm going to multiply it by minus 1 and add it to the second row. That's subtracting it. Just another way of saying the same thing. Yes? Row. So when I multiply this, I have, well, yeah, it's minus 2, minus 2, minus 2, minus 2. Right? And I put 1, can you see that angle? Come back over here. Minus 2, minus 2, minus 2, minus 2. Right? 1, 0, minus 1, 1. Right? This is a shear matrix, right? And I can always compute what's the shear matrix by taking minus this value over that value, and it'll tell me what the shear should be. But when I multiply this, right, I do this, and I get minus 2. This, minus 2. Here I get minus 2, 2, so I get 0, 0. So, because I'm doing this row times this column. So I can see why maybe you viewed it as a column, but it's the same as multiplying this row by minus 2 and adding it to this one. No, sorry, by minus 1, adding it to that one. People okay with that one now? I'm just doing matrix multiplication. Right, so. Are you okay? You look ready to ask and then... Okay, so so here's the shear matrix, and I multiplied them out. -1 times -2 is 2, plus 2 is 0. Right? So, and as I said, right, here I described it as a shear matrix. You could also look at this as just having two sets of equations, right, and in a matrix, and just what I multiply one row by, add it to the other to make this first item go away. That's what the shear matrix is all about. Okay, you'll see why when we get to high dimensions we want to have an algebraic and formulatic way, because it's way easier to program if I know exactly what to do. Right? In high school, what you did is you used your intuition. You looked at the equation, you said, "Oh, I see what to do." Your program, when you go to implement this, will not have that option. It will have to know what to do every time with very simple tests. Okay, so you're good with the first one. The second one is really the same thing, except we fill in a -1 instead of a 3. We get a slightly different matrix. I'll just come back over here. I'll do the same one. So our matrix now becomes -2, -2, -2, 2. Right? So I have to solve this matrix for x equals 0. So I'm going to compute a shear matrix, 1, 0, and again, here I'm going to take minus this over this, 1, 1. That's my shear matrix. And so if I look at this as A, B, C, D, the shear matrix here has always got minus C over A for this simple matrix, right? Minus this over that. Right? Gives me what this value is. In this case, it's -2 over 2, which gives me 1. Minus -2 over 2 gives me 1. So I multiply this out, and again I get 2, not again, 2 minus 2, 0. Because I add these two, I get 0. I add these two, I get 0. And I get something similar. So now I have to solve this. So I have to solve 2x1 equals -2x2. Oh no, sorry, equals 2x2. The minus was on the other side, so I have this 2x2 minus 2x1 minus 2x2 equals 0, right? And that gives me 2x1 equals 2. Equals 2x2, and so that gives me the values of 1 and 1 for my vector. Again, it's arbitrary. I filled in 1 for this one, and now I have to fill in the other one to satisfy this equation, which gives me 1 and 1, and then I normalize it, again, normalizing using the square root of the sum of the squares of the terms. After you have the vector, right? So because there's infinitely many vectors because of this scaling property, so then I choose it so that the norm of the vector is 1. That gives me a unique answer. 1, 1, and -1, 1. Or -2, 2, 2, 2, right? It would have been, depends on how you solve it. I got 1s because I got rid of the 2s in here, or I fill in a value of arbitrarily valued. Okay, so we will go through some more of these. So let's start with a simpler one, though, to give you some more confidence. How many fixed directions would the matrix 0, -2, -2, 0 have? You can work with a partner on this one. Okay, we got most of the answers in. I'll give you another 30 seconds. Actually, given I was going too fast, I'll give you another minute. How many people have no idea how to even answer this question? Okay, so let me tell you, the answer to this question depends on how many real eigenvalues it has. If it has imaginary eigenvalues, then it has, if both eigenvalues were imaginary, then it would have no real directions. Right? Or sorry, no fixed directions. So like a rotation matrix has only imaginary eigenvalues. In rotation matrix, these things just keep rotating. They go nowhere. Oh, we're getting a few more changes to our answers. So given that some people didn't even know what to try and solve, I will give you another 45 seconds after this. Okay, got 56 in, last call. Okay, slide. We lost somebody. There we go. Okay, so as I gave you a hint, the answer is it depends on how many eigenvalues it has. The answer is 2. It has 2 real eigenvalues. Somebody actually had this in the journal. I wanted to go over this one because they said the answer was 0, but they never explained why they thought it was 0. The answer is 2. So let's go through this. So eigenvalues, what do we want to do to solve for the eigenvalues? Somebody who's not... right, so we put lambda on the diagonal. We put lambda on the diagonal because they're zeros, right? Then we take the determinant, so we get the equation lambda squared minus 4 equals 0. We solve for that, and the roots are 2 and minus 2. Okay, you can just pull out the quadratic equation and shove them in there. So, if this had been, say, the matrix 0, minus 2, 2, 0, then it would have none, right? Because then we'd have lambda squared plus 4 equals 0, right? So if I made the one of the two minuses a positive, then when I do the cross product or the diagonal, so the determinant down this way, I'd get 2 times minus 2, so I'd get lambda squared plus 4 equals 0, in which case squaring the number has to be negative, right? So that's got to be an imaginary number to make that happen. Don't worry if you don't know imaginary numbers. We won't actually do much with them. They just know they happen to show up there. So the square root of minus 1 is an ugly thing. So is it possible for an equation to have only one fixed direction? Think about it. I write down this quadratic equation, right? And I said if it has imaginary ones, then that direction isn't there. So if I had b plus or minus something, and to get imaginary, I have to have minus 1 or a negative number under the square root, right? So if one is imaginary, the other's imaginary, okay? But there actually is one other case in which I have no direction. If lambda equals 0, then there is no direction, right? I don't scale, so there's no fixed direction, so you can have 1 as well. Okay, consider this system, minus 2, 8, 4, 4 equal u1, u2 equals 0, 4. What is the shear matrix that takes A1 to the E1 axis? That is, what is this shear you would use if I didn't pivot and I was trying to do Gauss elimination? This is one, I think people are struggling sometimes with eigenvectors because you're still struggling with the 2 by 2 matrix problem. You can work with a neighbor. see lots of people looking around for a formula. Right? This is actually one where you should be able to derive what this formula is. Right? You know what you want to do. Right? So it was up here a second ago, but I got rid of it. But you should just be able to figure out what this formula is because you want to multiply, right? Minus 2, minus 2, 8, 4, 4 by something. You know it's a shear matrix. I got to figure out what I put here so that when I multiply this column, I get 0 down here. There'll be something, something, 0, and something, right? So I can just look at those two columns and work that out. I don't have to try and memorize this particular formula. There is a formula for it if you like formulas, but if you're looking through your notes to find the formula, it's probably faster to just derive what you want to do. And if you've got an answer, since more than half the class is currently incorrect, at least with what you answered, it could just be random starts, but how do you check your answer? Just multiply them. See if it does the right thing. Now, actually, somebody down here said that. Was that you or Michael? You. Okay. I wasn't sure who said that, but. Okay, last call. We'll give you another 30 seconds. Okay, it's not last call, it's 30 seconds. Again, you got 30 seconds. Check your answer. Last call. Okay, so before I go over the answer again, as I said, I'm trying to give you a hint. Yes, there's a formula in the book. I never remember this formula, but it's also not that hard to derive, right? I got to figure out what I'm going to multiply. So I'm going to do my multiply like this, right? So I'm going to do whatever. So this one's always a 2. I don't actually have to worry this top row because of I'm going to multiply by 1, 0. This top row is going to be minus 2, 8. So that didn't actually change. But this bottom row, I'm going to multiply something by minus 2 plus something times 4, and I want it to equal 0. Right? So what do I have to multiply minus 2 by, so when I add it to 4, I get 0. Minus 2 times 2 plus 4 is 0. So the answer was D, right? 1, 0, 2, 1. Right? Now I can check my answer. I can just take those and I can start doing the multiplication, and I work them out, and I will get that I get minus 2, 8, 0, 20. Right? So again, it really comes down to I want to figure out what to put here so when I do this, it goes away. So there is a formula, and I think it's like minus this divided by that. So minus 4 divided by minus 2 is 2. Okay, another really quick one. 30 seconds, just on your own. Come on. What is the name of this equation? Okay, last call. Missing somebody, but okay. Okay, so this one is the characteristic equation. Okay, so a number of people were distracted by the eigen in eigen decomposition, and a few were by d-eigen theory, right? No, this is the characteristic equation, page 137 of the book. Okay, anyone know what is eigen decomposition? There is an equation for eigen decomposition. Okay, so the book writes this as the eigen decomposition. What's R? Somebody else? Sam? So this is the matrix of eigenvectors. Okay, so this is another geometric interpretation, which is I can view my matrix A as a rotation. The eigenvectors, if I've orthonormalized them, so their unit size, are a rotation matrix. They rotate things. Then I scale the axes in some way, and then I rotate it back. So if we think back to that original phoenix, let's just jump back and do that. That's on the slides I was missing. But in this phoenix, oops, back, draw it, right? We can think of our two eigenvectors, 1 over the square root of 2 over the square root of 2, right, as a rotation matrix. So I take some vector x, I rotate it. In this case, that rotation actually does nothing because I started with a circle. I rotate it, doesn't really do much to the circle. Then I apply lambda, which scales it by 3 in one unit and 1 in the other. And then I rotate it back, which is why that thing looks like an ellipse, because I just rotated it, scaled one axis and not the other, and then rotated it back into place. So that's the eigen decomposition. And let's talk a little bit more about that one. Come back here later. Oh, another quick engagement question. Okay. So this one again, do by yourself. It should be quick. Considering the following matrix where A, B, and C are real numbers, what is true about this? And D is a statement about anyone's ability, not yours. Mm-hmm. You want to write it like this? Like that? So the because of the properties of these, so this is an interesting, right, extra thing. If I multiply this equation, you go from here to here. So if I multiply A times R inverse, so actually, when you multiply A by R, so we'll get there in a second, right? That's the same as R times R inverse lambda R. This becomes the identity matrix. So now I do R A R inverse, and that's lambda R inverse, and these cancel out. So the two equations look almost the same. The only difference is the inverse. Okay, and for an eigenvector, because it's an orthonormal matrix, the inverse is actually just its transpose. So it is possible, because I get this part wrong, whether it's this side or that side, but you can view both of them the same way, right? So does anyone have their book open? Is the inverse on this equation in front or this equation in front? Because I never remember. It's like this? Okay. Like that. Okay. So I'm dyslexic, right? So those little things are hard for me. But the basic idea of a rotation, so both of these are rotations. One's rotation, we had this whole discussion last class, and somebody correctly corrected me because I kept saying it was clockwise. So this is something, as you work with libraries, by the way, be very careful. Some software libraries will define the rotations clockwise, and some libraries will use it counterclockwise, which is why I keep thinking it's counterclockwise, because the library I use most often rotates counterclockwise. And that's because in some coordinate systems they use left-handed coordinate systems. So if I rotate counterclockwise in a system that's like this, right, into the screen, and you come out of the screen, then it rotates clockwise when you're looking at it, but not clockwise when it's in the right math formula. So it's the same kind of thing here. Sorry about that. So if I got them wrong, you get extra points for correcting me. Okay, so most people now have the answer to this. Real and symmetric. So in fact, I asked you a question earlier where, like, how many fixed directions were they? That matrix was symmetric and real, right? So you could, without even computing the eigenvalues, I asked, like, did anyone solve it a different way? Right? You could solve that one by saying, oh, look, it's a real symmetric matrix. For real symmetric matrices, the eigenvalues are always real. They have this eigendecomposition representation, and they allow for stable, efficient numerical. So C was the correct answer for that one. One more before break. What are eigenvalues of the following matrix? Okay, and this, by the way, is not a question I made up. This came courtesy of one of your fellow students. Okay, oh, by the way, they said I should only give you 30 seconds. You can talk with your neighbor. And I will not divulge the name of the student who suggested this. Okay, I'll give you another 30 seconds. Okay, last call. Okay, so the correct answer for this one was B. Okay, this is upper triangular, so the characteristic equation for an upper triangular matrix or a lower triangular matrix becomes pretty simple. Right? If I have A minus lambda, B, C, D minus lambda, I get A minus lambda, d minus lambda minus bc. But when it's triangular, either lower or the other side, right, this goes away, and this is my equation equals 0, right? And that actually tells me that a and d are the values of lambda that make this equation equal 0. I can just read off the answers. So if I have a diagonal matrix, or an upper diagonal matrix, or a lower diagonal matrix, the eigenvalues are what? The values on the diagonal. So I just read them off. So you didn't have to worry about multiplying by those weird numbers. So after you've sheared it, you can, but you can't, because the shear matrix changed the eigenvalues, right? So when you sheared it, you multiply by something. So the matrix you get after shearing always has this properties, but now you have to know how to account for the other matrix, right? So it's not quite the same. Engagement question, and then break. Be back by 9:40. Yes. Yeah.
I wanted to change my seat to there. You said my name and thought I was over.
Yes,
in
because
that
it's
section.
yeah.
I'm actually over there.
Over there. So, and your name is
Bryce.
Bryce.
Yeah, young. I don't know.
Okay.
All right, excellent.
Chris hasn't recreated the program when he showed us another follow.
Send him another follow-up. Yeah.
Thank you.
I don't think I ever got invited to the class on GitHub. Because on the last assignment I wasn't in it, so I just shared it with you and the TA and submitted it.
My
also.
guess is you have, but lots of other people, like it goes, you have to, when I send it, you have to go look in your spam bucket, because that's probably where it's going to go. So what's your email?
MUN@UCCS.
M-
UH.
Yep. You've actually sent it twice, but we'll
I must have
send it
just
to you
missed it.
again.
That's my bad.
No, it's okay. So because it goes in your spam bucket, right, you don't
Yeah, I
necessarily
didn't
see it,
check
right? So.
Thank you. values to get different matrices and bring those matrices to share those matrices. What I'm confused about is how we reach that particular equation.
Here?
Yeah.
Okay, so I said, so sorry. When I do, because I normally go to what's called row echelon form. When I shear, instead of just trying to make it so that there's a 0 here, I try and make that one a 1. So I don't use a traditional shear matrix. It's a more complicated process that we don't teach, but it's what I always do. So this I just divided that row by 2, right? That part's it. And then, so do you see how I get the 1 minus 1, 0, 0, or not?
With the shear matrix, right?
Well, so not quite with the shear matrix. So when I have 2 minus 2 minus 2, 2, right? Instead of multiplying by the shear matrix of 1, 0, minus 1, 1, I actually multiply by this result with this. Because I want to multiply this one go to 1 and this one go to 0. It makes some certain math easier. So when I do this, I get here 1 minus 1, and then here I get 0. So this is not the book of the shear matrix. And I keep forgetting that because that's not the way I learned it, so I refer back to my early days. So with the shear matrix, I have got this. And here we have 2 minus 2. Right, yeah, it's just right. That's what I have. To solve this, x equals 0, I still have the same problem. That I can put any value I want. If I use it x1, x2. This value is arbitrary because this row doesn't do anything. Right? So that's why I just say, okay, let's say this is equal to 1. Now that I know this one is equal to 1, they just made it up. Now, what's this one got to equal to make this equation work out? And that if this is equal to 1, then x1 must equal to 1. Because I'm going to have x2 plus x1. So because of these are both 0, this is where it's not normal. This matrix is now singular. I can choose any value I want. There's infinitely many solutions. So I choose the one where x2 is equal to 1.
So 2 times x1 plus -2 times x2, which is equal to 1 is equal to 0.
Right. And I solve that for x2, and then for x1, I get x1.
And then we normalize that because
We want to have, so if I want to use that rotation matrix interpretation, I need it to be normalized. That's one reason to do it. The other is that there's a unique answer. So if we're on the midterm and you forgot to normalize, like if there's a 10-point question, it was like 1 point for normalized. It's not a big deal, but we want you to normalize.
normalize because I'm sorry, I completely lost focus there.
It's like, we normalize for 2 reasons. One, it gives us unique answers, so there's always a unique eigendecomposition. The other reason, and maybe the bigger one, is if I want to use the eigendecomposition where I think of it as a rotation matrix, scaling and rotation, then to be a rotation matrix, it has to be orthonormal. So it has to have unit vectors in it.
All right.
Okay.
So
go ahead, no.
just ask you a quick
Of
question.
course.
So on the homework or the program,
Mhm.
you know how it says if they draw a line that's parallel or it's illegal for whatever reason, does that line count for the other parallel lines? Because I know you just don't draw the line, but
So
can you play one that's parallel to the illegal?
once a line is parallel to a line that's already been played,
Well, I was
not
more
gonna
thinking.
change.
I was more thinking about if you play in a column that was already played in, like if. You,
oh yeah, so that's a good question.
Yeah.
So if their play is invalid, then the start and end row doesn't count
So
because their
then
play
you-
was invalid.
So then you don't count that as a parallel line to check against.
Well, so if there's already a line that's parallel to, then whatever line I add later that would be parallel to
Well,
this
yeah.
would also be parallel to the first line, so it doesn't matter.
Yeah, but
But it
here's. Let's imagine that you're playing a game and you put one here and then one here. and then you start in this column, but you go that way, and then that moves illegal because it starts in this column. What happens if you try to play one that's here to here, same area, like same slope as the one
Yeah,
that was
so
illegal?
plays that are invalid count neither for parallel, start, or end.
Okay, so I didn't mess that up. Okay, I'll fix that.
Okay, we're going to get started again. So first, during break, I was asked a couple of questions about the assignment. So for your design today, none of this will matter, so you don't have to go back and change your design docs. But for the way the game is actually played for next week, if a player's move is invalid, it does not count against the test of the k previous moves, start and end blocks being invalid, rows and columns being invalid to use. So once a play is invalid, right, it's like it never happened. So you don't have to worry about the start and end blocks they used in an invalid play when you go back k, which is the second number. That was the other question I got, right? So the first line is nk. N says the size of the board. K says how many previous turns do I look at to check whether or not I'm allowed to use those rows and columns. Well, actually, it wasn't clear. It didn't say what happened when a move is invalid. It did say that? Okay. No, okay. So if it said that, then even if it's invalid, you get to count it. That makes it easier to program. So I simplified the rules to make that a little bit easier. So again, the game was sort of hokey anyhow. It's actually based on a real problem, but I can't talk about that problem. But it's not really a game. It's a placement project for a military contractor. You can describe it that way. Okay, so yes, stick with what's written there. That's a minor rule of the game. The real point here is, did you handle like all the math stuff right? And did you at least check the previous thing? It'll just be a little harder for the TA if we have inconsistent interpretations of the rules. And if you, I updated one of the files, p2.txt, from when it first was, because the entire play kept referring to column 5, but I accidentally typed 4 something, right? It's now 5 something. It's supposed to be a 5x5 board with both examples I gave you were 5x5 boards. So don't use the old version. I will probably post tomorrow or, no, not tomorrow, Wednesday or Thursday, I'll post 2 more tests for your program to have to work with, but I haven't made them up yet. So. Okay, so in words, describe the action of this linear map. This one you should do on your own. Shouldn't take very long. I'll give you 45 seconds more. Okay, we've got most of the class going down the garden path in this one. This question is trickier than you think it is. And as a dyslexic, this is probably a question I would hate if I was in your seat. Most of you are still wrong. Rethink your answer. Okay, well, we got most of the answers in. We'll go ahead and call it on this, even though most of you are currently incorrect. Last chance, Monty Hall. Anyone want to choose a different door? what's the right? So let's make sure we understand what's the name of the E1 and E2 axes, right? So E1, right? So one way of thinking about it is, right, when I have my vector, right, I write E1, E2. Right, so if I want to go to the E1 axis, right, in my matrix, right, when I get rid of this, we talk about shearing and Gaussian elimination. We are shearing stuff to the E1 axis. Okay, last call. Oh no, that's not helping. I have. Okay, so this is a shear in the E2 direction. None of the above is a valid answer. And in case you haven't noticed, it is still running. I said it was a tricky question. Afterwards, it's like, yeah, so the answer is not B. If you answered B, go for a different choice. Okay, 4 of you are not paying attention. Okay. Okay, consider the determinant. What is the determinant and the eigenvalues of this matrix C? Do this one on your own. It's this is diagonal, but yes, that's also upper triangular. So diagonal is a special case of upper and lower triangular at the same time. Again, E is a statement about no one can, not your abilities. Does this matrix scale? Yes, this matrix scales unequally and by -2 in the E1 direction and 0.5 in the E2 direction. So scaling by minus is also sort of a flip, right? Because I scale and flip, scale and flip.
Multiply this matrix by a scalar and get the same effect.
Can you multiply? So if you multiply it by a scalar, you will get a magnified effect, not the same effect. So if I multiplied this by 2, then I'd be having -4 and 1, and when I scale, I'd get 4 times the x direction. Or the shapes would be similar, but they'd be scaled versions of each other. Okay, last call. Last call. Did everyone not come back from break? Okay, well, most people did get this one. The correct answer was A, right? So first, the eigenvalues can just be read off. The eigenvalues are -2 and 0.5. And the only question between A and C was, what's the determinant? And what's the determinant? Well, it's AD minus BC, and BC is 0, so it's A times D, and you get -1. Okay, what is this equation called? It's gone. Reminds me, I was going to check make sure I had this right or wrong, but now I have to look it up. Okay, so last call. Most people did get this, and I did go back and check, and I get this is in the right order. So the R transpose is the same as R inverse, so you can relate them on either side. So, okay, so the correct answer was D, eigendecomposition, and C is not quite right. When you get done, lambda, right, is the diagonal matrix of eigenvalues. Okay, so in a sense, you could make this diagonalizable, but the real answer here was eigendecomposition. Okay, really quick question. Do this one on your own. You have 30 seconds. I'll give you a hint. It's sufficient to compute the first part of your answer. You don't have to compute everything. That's why I'm only giving you 30 seconds. And again, E is a statement of everyone or any ability, not yours, since we got a couple of those. Oh, got more of those. Okay, well, we're at a minute. We only have 45 answers. These should be pretty easy to do. I'll give you another 30 seconds. So I don't want to. So on the midterm, if you get these kinds of questions wrong, you get a 0 for the midterm. Doesn't matter how much else you get right. You have to be able to do the matrix multiplication questions we will have. So if you are struggling with these, you need to practice. And looking at the answers, many of you need to practice. So you can find online calculators for like matrix multiplication and calculators for even eigenvalues. If you want to practice and you've gone through the book and you want more practice questions, just Google matrix multiplication calculator or do it in Excel, because you can do it in Excel, or write a little program. But, last call. Okay, so many of you are in serious trouble for the midterm, right? Because the second most common answer was B. Who can explain why it can't possibly be B without doing any calculation? Hannah. Well, B, Okay, that was C. Okay, but that's okay. You answered for C. Why it can't possibly be C? It also can't be B, right? So this is a 3 by 2 times a 2 by 3. The answer must be a 3 by 3 matrix, meaning your answer was down to A or C. Okay, and then if you just go ahead and line them up and multiply them out, you get the answer is, sorry, D, not C, D. Right, so the answer is D. Okay, but many of you came up with B, yes. So if I multiply B times A, well, the shape would be right. I don't know that the numbers work out, but let's see. 2, 8, 12, sorry, 12, 14. Yes, it looks like it works out. So that's just B times A. So not quite as bad, but you've got to get the order right. So again, what I recommend if you're really good at this, you just want to plug through it without writing them out. But if you write these as A, B, right? I'm going to multiply A times B. Write an A here and the B up here, so they're in the same order left to right, and then do your multiplication this way, and you'll get them in the right shape and the right order that way. Okay, so another question from the journals. What kind of matrices can all quadratic forms be represented as? So this chapter had a whole section on these quadratic forms and interpreting things. Okay, I'll give you another 30 seconds. Okay, so this one's pretty close in terms of our votes. Last call. So who wants to defend the answer A? Good, it has no defense. Who wants to defend the answer B? Nah, not there either. So how about D? We got a lot of D's. Joseph. Okay, so yeah, so the correct answer is C, and C is more correct than D, right? Yes, it is a 2 by 2 matrix if it's a 2 by 2 symmetric matrix, but 2 by 2 symmetric matrices were described in the chapter as what we're looking for, and there are 2 by 2 matrices that are not symmetric that do not describe quadratic forms, right? So that's why we want the answer to be C. Okay, another quick eigenvalue. 2, 1, 1, 2. Find the eigenvalues. Do this one on your own. Don't work with a neighbor on this. Okay, going slower than I thought. I'll give you a few more minutes. Okay, I'll give you another 30 seconds. Okay, last call. Okay, so most people did get this. Again, we do our 2 minus, we're going to start with this, get our characteristic equation. So we get our determinant of 2 minus lambda, 1, 1, 2 minus lambda equals 0. That gives us lambda squared minus 4 lambda plus 3 equals 0, for which the roots are 3 and 1. So the eigenvalues are 3 and 1. Yes, lambda 1 by convention is the largest or the dominant eigenvalue. So we always reorder them to put the largest one first. Largest in absolute value. If it's negative, it can still be the first one, but largest in magnitude. Any questions? Do I need to go through this in more detail, or is that okay? We actually have already covered this one earlier in today. So if you missed it, go back to the beginning of the video. So quick engagement question. Last call on that. Okay, we have enough disengaged. I'll go ahead and ask this. Am I going too slow, too fast? Clueless, don't know. Didn't open. Interesting. I have more answers to A, B, and C than I had people who said they were disengaged, but that makes this more difficult to interpret, but okay. Last call. Okay, another journal question. Given A1 transpose is 4, 6 and A2 is 2, 8, what is the dominant eigenvalue of A? You can work with a neighbor on this one. By the way, when I select your question, you get some class participation points for having good enough journal questions that I select your question. Because yours isn't chosen doesn't mean I don't think your questions are good enough. I also balance that out for people who have a good question and currently don't have much class participation points. So, yes, Joseph? Yes. So, but if I might have also taken off points if you get your own answer wrong, so I don't remember. But sometimes they change the value to make the question more interesting, or because to get the answer, the question was not quite right. I was going to go format the answer better, and I forgot to freeze it. Okay, we got most of the answers in. I'll give you another 45 seconds. By the way, on these eigenvalue ones, if you're done, you're bored, because some of you said I was going too slow, you can always compute the eigenvectors for a little bit more practice. And then check your answer. Okay, last call. Okay, so we got a couple of answers that surprised me. So who can explain how you got B, 8? This isn't random guessing. It's unlikely 12 people guessed B. I don't know how to get B. It's not the right answer, but I'd like to understand how, if so, there's some process you got there. But the correct answer is C. Okay, so first you write the matrix, so it's A1 transpose, that's the first column, 4, 6, and 2, 8. How many people wrote the matrix the other way? 4, 6, 2, 8. Okay, did it make any difference? No. In fact, taking a transpose won't change the eigenvalues. It will change the eigenvectors, but it doesn't change the eigenvalues. And if you think about that, that's because if I do the transpose, right, I'm doing the determinant of the diagonal stays the same. I have A minus lambda, D minus lambda, and then instead of subtracting BC, I subtract CB. It doesn't matter. Yes. Either. Okay, I see why. So a small algebra mistake when you're solving for the roots. Okay. So just to make sure people write, so we put in our minus lambda on the diagonal. Doesn't matter what order I put it in, right? So I get my polynomial of lambda plus 4 times lambda minus 8. I got to multiply that all out. When I multiply that out, I get my two roots of 10 and 2, right? So again, you can use the quadratic formula. So that's one that you should definitely have in your notes for these eigenvalue sections, B, b squared plus or minus the square root of 4ac over. Okay, what is the largest eigenvalue? What is the eigenvector associated with that largest eigenvalue? Right. So, right. Oh, let me actually make this a little bit easier. I'm going to make sure I have the matrix going along, just so you don't have to look back in your notes. So here's our matrix. We want to know the eigenvector for that matrix associated with the eigenvalue, the largest eigenvalue. The eigenvalues were 10 and 2. You can work with a neighbor on this one. See, wow, everyone's done already. I forgot to start. Most people have an answer in. We'll go for 45 seconds more. How many people are still computing or working? I'll give you another 30 seconds then. Hustle up, yeah. Okay, last call. Last call. Okay. Okay, so we're going to start with lambda equals 10. We put that into our matrix. We get minus lambda plus 4, 2, 6. We get the matrix minus 6, 2, 6, minus 2. Okay, so I'm going to again shear that with minus 1. So with d equals minus 1. Now I keep forgetting because when I learn this, I do it with row echelon form. So I'm not going to shear with that matrix. I'm going to multiply by a matrix that also makes the top row go to have a 1 value. So actually I'm going to use the matrix 1, 6, 0, minus 1, 1. So when I multiply it by that, I get a matrix that looks like 1 minus 1/3, 0, 0. And that gives me, again, a choice. So it's unconstrained. So if I'm going to in this case, when I do these, I like to choose something that makes it easy. I'm going to put in V2 equals 3. Right? I'm going to do that because when I look at this, I see the 1/3. So if I put in a 1 here, then I get like some other complicated number up there. If I put in a 3 for this one, I get a 1 for that one. Dang. Okay. I got to keep putting that none of the above up there in case I make those kind of mistakes. But yeah. What was I thinking? Well, so that might just be I wrote the sheer. Okay, so let's go back. We're just going to completely ignore this question. I clearly was doing this too late last night in the back. Yeah. So this is because I cubed it instead of squaring it. It was too late when I was making up these slides last night. So it's just scaled wrong, right? So it's not normalized. So engagement. How much do you like the fact that I just got one wrong? But yeah. So I guess it should be also one here, right? So there's another process that I learned linear algebra using a different process. So I just keep always using what we shear to row echelon form instead of a traditional shear. We make the first item of the matrix. So that's why when I do these, they always come out with a 1 up here because that's the process I use. It's the way I learn things, and I forget that. But clearly last night I was not thinking very well. It was too long a day. So we will skip when I get this done. So We'll just skip over those. So we're now going to, we got a couple minutes. I was going to skip over to some other questions. Come on, where we go. Nope, not here. Okay, which of the following performs a reflection about E1? This should be pretty quick. So this is somebody's clicker question, but well, we'll go over it in a second. Okay, got most people have answers in, and we have pretty much a tie between A and B. So, right, who wants to describe why it's A? We got like 20 of you. Or was A just a guess? So A is a reflection, but what's it a reflection around? So we can think of it here. So I'm going to take two vectors, right? This is 1, 0, 0, 1. I'm going to multiply them by the matrix. So we got 0, 1, minus 1, 0 times 1, 0, and I'll do it by 0, 1. So we're going to multiply these out. So 1, 0 becomes 0, 0, minus 1, 0. And this becomes 1, 0. So what used to look like this now looks like that, right? So actually, so the first vector is now like that, 0, minus 1, and x, y, 0, minus 1, and like that. So we flipped it over. That's a reflection around minus 1, 0, minus 1. That's not a reflection, it's a rotation. Okay, the second one, that's A. B, we're going to multiply, we're going to do it with, what's B? 1, 0, 0, minus 1. So that gives us 1, 0 goes to 1, 0, but this goes to 0, minus 1. So this is going to go to 1, 0, and like that. So that's a reflection around the E1 axis. And the answer was B, which many people got. Okay, so which of the following is a non-trivial homogeneous system? Do this one on your own. This is as much terminology as, I'm not looking for the answer. I'm just looking for you to say which of these is a non-trivial homogeneous solution. Okay. Okay, I'll give you another 15 seconds. Last call. Last call. Okay, so we have two pretty equally split answers. That's the distribution. So who wants to defend why the answer is E? There are a couple of you with E's. Anyone want to defend that one? Wild guess. Yes, E is not even an invalid form. There are no variables, right? So this is a clicker question from one of the students. So the semicolons are their way of saying end of the row, I guess, right? Right. So this is first row 2, 1, 4, 6 times 1, 1/2, right? Equals 4, 4, right? That's not even true. It's just a bunch of gibberish. So it's not E. So the two most common answers were C and D. So what's the definition of a homogeneous system? In the back. Can you speak up? So if both vectors lie on the same direction, that's a degenerate system or a system, an inconsistent system. But it doesn't have to be homogeneous. What does the homogeneous mean? So the last part is equal to 0. So anything of the form AX equals 0 is homogeneous. So homogeneous, think of the O there, right? That's what makes it a homogeneous system, right? So the O's, right, give you a 0 there. So the answer is C. Okay, another review question. Given P25 and Q454, give the parametric form of the line T that connects P and Q. and you can work with your neighbors, since lots of people are. This is long enough ago. You shouldn't have, when you get to the midterm, which is a couple weeks away, right? You won't get to work with your partner on the midterm. Okay, last call. We got most of the answers in, or sorry, another 30 seconds, not last call. Okay, last call. Okay, most people did get this one, right? We take Q minus P minus Q times T, right? Work that all out, and it's 5/4 plus T times minus 301, right? Which is E, none of the above. A couple people were suckered in by C, where I have a -3 -1 instead of a -3 1. I have no idea how people considered either A or B. They have absolutely no relationship to the problem. D was at least somewhat tricky because it had the 2, 5 and the 5, 4 in there. But you don't just put P and Q in. You have to take P plus Q minus P or Q plus P minus one of them plus the others. Right, a very wrong point, right? The point's not on the line, right? So okay, one last one for today. So do we go to 1040 or 1050? 1040, okay, that's what I thought. So I somehow keep putting the wrong thing on my phone. But so assuming the coefficients of a line have already been found as the first coefficient, A is -38, B for BX2 is 44. What must C be in order for the point to exist on the line? Do this one on your own. Okay, we'll give you another 20 seconds. Okay, last call. Okay, so I see some of you were suckered into the answer D equals 6, which is almost there, but you solve this, you need to have AX1 plus BX2 plus C equals 0. And if I put those numbers in, minus 38, 44, they add up to 6, so I have to subtract 6 to make it work, and the correct answer was C. So, last engagement question, and then you can go. Last call on engagement. I'm going to do the why were you disengaged question as well. So if you're engaged, you can ignore it. But if you're disengaged, I'd like to know. Last call. Okay, for those who were disengaged, why were you disengaged that last couple of minutes? Those were all review questions, but... Yes.
Should we just turn in the documentation
Yes.
for right now? Get also, so looks like this has not.
Yes.